But now I understand. I just didn't realize that was sulfuric acid. I don't know why I didn't do that.
Yep,
But
nope,
thank
nope,
you.
that's sulfuric acid. Yep, and if I ask you to draw it out, you shouldn't be able to do so.
Yeah, of course. Thank you so much.
Sure,
I have a question about the aromatic substitution homework.
sure, I have everything open, I think. Except it's hard to get to. Um, Aromatic substitution homework. Okay, which question?
So I'm confused about 3B and E.
1, 2, 3. 3B. Okay, this is a typical problem. First off, I don't know what you're specifically asking about, but let me take it from the beginning. You have two aromatic rings. They can communicate through resonance between the two rings. But to start off, you consider them separate. You have a deactivated ring and a ring that's not particularly activated. So the one on the left is going to win. So all the reaction will come from the ring on the left. It's just the more reactive ring. Okay.
So would you say that a benzene ring is activated or deactivated?
Okay. Well, biphenyl, just the two rings, no substituents, is more reactive than benzene. The question is how much electron withdrawing can you put on the right-hand ring before it becomes deactivating? And I don't want to go there. I intentionally put this acetyl group meta so that any sigma complex that can go in both rings, the positive charge would have to be here to go in the right ring, and it'll skip that.
Right.
Okay.
But you're saying that the ring on the left is more activated than the ring on the right.
Yeah, it's more reactive. There's nothing activating it except maybe the other aromatic ring. Okay, and I would say the right-hand ring is still activating because this is meta. If this were para, it'd be much harder to decide. But, any resonance structure adds something.
Right, because I was thinking that, I don't know where I read it, but I thought that benzene was deactivating. So I put that, so then I put it.
No, I believe it is weakly activating, just like an alkyl group. The part of the problem with the resonance here is the two rings have to be coplanar. And if these aren't all four hydrogens here, ortho, then you have a steric problem.
Right, yeah.
So, there's, it's more complicated, but the approach, for, excuse me, any exam, I would give good credit for any reaction the left-hand ring. If you gave meta instead of orthopara, I still give you 2 points out of 3. Usually that's 3 points.
Because I put it meta.
Yeah, no, that's not a bad answer. I'd argue that orthopara is better, but the tricky thing is when you put something like if you had a para-nitro group here, I don't really know the answer. Whether that would still make orthopara or whether it might want to go meta. You're likely to get a mixture.
Okay.
Okay. So the common problem here is people will look at it and say, oh, meta director, it goes down here, without considering that the other ring is more reactive. That's the main consideration here.
Right. So would you say, is a phenyl group always more reactive than, because like with part E, with E, I put it on the right ring because NH2 is like.
Okay, well, E involves another consideration. Mm-hmm. You throw anything in sulfuric acid that can be protonated, it gets protonated. So that's what the comment is in the answer key here. This nitrogen is protonated. This is a highly deactivated ring.
Oh, so anything that can be protonated.
Yeah, sulfuric acid, it's you don't want to put it on you. It's nothing but acid. There's no water in it, right? Fuming sulfuric acid is beyond no water. And so that amine is going to be nitrated very quickly. Your book, I believe, says aniline doesn't nitrate, but you can force it to nitrate. You can make meta-nitroaniline by nitrating aniline directly, which is on another, which is on one of my slides. Haven't woken up yet.
No, but like if NH2, because that has a lone pair, so isn't the rule that that's the ring that's activated? So that's more activated than.
You've got to think a little broader than that. You got to think what else might happen. Okay, you've got a reasonable base. Anilines aren't strong bases, but they're certainly basic. And you got a very strong acid, sulfuric acid. It protonates first.
Okay.
Okay. So now you're looking at sulfonylating an anilinium cation. No lone pair left. Okay. Yeah, the real, I should mention, if you haven't picked it up, simple acid-base reactions are some of the fastest reactions known. I mean, they are the fastest. There's nothing faster. Other things may be just as fast, but nothing faster. So the protonation here would be instantaneous on mixing. The sulfonylation will be a little slower, and the sulfonylation will attempt to happen on the anilinium cation, not the free aniline.
Would only fuming sulfuric acid protonate the aniline?
Any sulfuric acid would.
Okay, got it. Thanks.
Yeah. I've got a question here that's been hanging for a while, a couple. Slide 21. Let me pull this out. Slide 98, there's a question. So I don't want to lose the ones in the chat. Some people are too shy to speak up, or, you know, maybe they're having a microphone problem. Okay. Yeah, this is a follow-up on a previous question. You've got to assess all the constituents and what they prefer, but the most activating or least deactivating will generally win. So in the middle one here, the carboxylic acid is saying, I want it here, I want meta, but it's a fairly deactivating group. The bromine is only weakly deactivated and stabilizes the intermediate cation, which is the important part here. So it wins. So you're going to get ortho and para to the halogen, the bromine here, tough luck carboxylic acid. Okay, that's the way it generally works. Okay, Keyshawn?
Can you hear me?
The rule is when you have an activating group and a deactivating group, you ignore the deactivating group. Okay, that's the general rule. Okay, and you know, the more complicated you make it, the more you're likely to get something unexpected. That we're going to go by just the basic rules. Okay, so go with the most activating group. You know, and I'm not going to give you nitro versus ester, you know, the carbon of an ester. You know, we're not going to go be that picky. Jackie, do you have your hand up?
Yes, I did.
Hard to see it's you. You've got the sun behind you.
Yeah, I'm at my parents because
Oh, that's okay.
changing environments for today.
You can be in semi-disguise.
Yeah, I've got my mom's shirt on. It's my sister went to Ohio State. So.
I went to Ohio State for one summer to do undergraduate research.
It's a really beautiful school.
Oh, it's a beautiful campus. I used to love to walk around, and I spent as much time there playing ultimate frisbee, I hate to admit.
So I guess I was just adding on. I guess I'm getting hung up on the aromatic substitution because I have to remember what the resonance structures look like to really appreciate why we direct the way we do.
That's what it's all about.
So number 3, which it was C that we went over.
On the homework, yeah.
I guess we were talking about where we would place the sorry. So we know that the left ring is more reactive.
Talking about 3C?
Yeah, 3C.
So the right-hand ring has the oxygen on it, right?
Right. So I understand that the right-hand ring isn't as reactive, so we're not really going to react there.
Now, are we looking at the same thing? 3C.
No. Sorry. It's
Oh, that one. B.
B.
Okay, yes.
So we do better with placing substituents at the ortho and the para positions because we don't end up with a resonance structure in which there's a positive charge at the same carbon alpha to the carbonyl group, because that doesn't work.
Well, the way I positioned it, it's impossible to have a cation in the left-hand ring that's stabilized in the right-hand ring, no matter how you do it, with that carbonyl group in the wrong place. If you have, let me take
even if you do a meta, even if you do it at the meta position.
Yeah, let me put this into ChemDraw and I can make it clear. Words don't do justice to Orgo, right? So if you attack it meta, I'm almost awake. Okay, if you attack para, I should say, it's what I just drew. Let me do the same thing I did before. The positive charge can be there, and there. And this charge can now go here, here, and here. So you get resonance in the right-hand ring, and I'm arguing that's going to help you to some extent, even though the right-hand ring is somewhat deactivated.
But if we attacked meta, we would get positive charges.
Okay, if you attack meta, now you get the positive charge on the alternate carbons. And if you look to see what carbons can carry it, those are the 3 carbons, and none of them can go into the other ring.
Oh, okay. So the best answers are ortho and
Ortho and para are the best.
Because my answer, I did a mixture of ortho, para, and meta, thinking that all 3 are possible.
Yeah, they're all possible, and saying meta is not a bad mistake. I mean, it's certainly understandable, but in general, a phenyl ring can stabilize through resonance to the other ring.
Okay, thanks a lot. That makes sense.
Yeah, now, if I were going to be extra mean, I know you guys often think I'm extra mean when I write exam questions. and I ask you about this system, that is definitely not more reactive than benzene because this cannot lay flat. You cannot have resonance from one ring to the other. These methyl groups are just knocking their heads against each other. In fact, this molecule, well, if you make these different each side, let's make these, oops, dimethyl dichloryl, that's capable of chirality. But chirality in that extent is not on this exam. You know, that's a trickier one. One of the ways you can get chirality without a chiral carbon.
So if you remove the chlorines, then where would you get the electrophil attack?
Well, if you like this, or with the four methyl groups all still there.
Yeah, with the 4 methyl groups.
Well, you know, it's symmetrical. You have, I would ignore this completely. You have these 2 methyl groups, and they're saying here and here, right? So you get ortho and para to the methyl groups. And if you think about para to the aromatic ring, you're going to put a positive charge next to an sp squared carbon. So the presence of this aromatic ring will deactivate the para. The methyl groups are activating their ortho or para, which is meta to the aromatic ring. So yeah, this is a bit beyond. This is a good homework question. I don't think it's a good exam question.
Okay, thanks.
If this were an exam question, it wouldn't be in the regular reaction dip at the end, and I'd say, hey, pay attention here. We got something else going on.
Hello, Professor. So you mean that if this one react with something like HNO3, H2SO4, for this reactant still okay, put in the meta. No, sorry, order.
Well, you got to be careful the use of ortho, meta, and para. You got to say ortho to what? It's ortho to this methyl group.
Okay, order to the methyl group. Okay.
Yeah, that's the product I'd predict out of here, and there's only one mononitro compound I'd predict. The para is activated not by the 2 methyl groups and not by the other aromatic ring for the reason I just stated. Okay.
I see. Thank you.
So I'm like, I don't know
And
why
somebody has your hand up. Is that you?
No, it's me. I'm just a little confused. Like, I'm not seeing, like, I'm trying to do like the arrow pushing for like the resonance where it like goes into the other ring. I don't know why I'm like not seeing it. Like, I see it around the ring itself, but how does it like go into the other ring?
Okay, let me actually draw it in the top one. I'll let you try to draw it in the bottom one. You'll get frustrated because you can't do it. So I'm just going to draw the resonance structure here. Where am I? Okay, and so you just need a simple arrow. Now, do it this way. Whoops. There, like that. And it's going to end up where the black dot is. So you're going to get a double bond between the 2 rings.
Okay.
Which is why they have to be flat, which is why you have to worry in a more advanced setting about interactions with the ortho hydrogens, ortho to the ring, to where the 2 rings are attached.
I'm sorry, Professor, can you repeat the resonance structure again?
Yeah, let me draw it just to be clear. When you get resonance from one structure to another, you're going to get something like this. The one I just drew. So forget the substituents. The one I just drew would be this resonance structure. Does that help?
So we don't need to consider the substituent here?
Consider, I'm sorry, what?
We don't need to worry about the carbonyl group when doing the resonance structure?
Well, it would, if you put the carbonyl group, what am I doing? Here, it would have a much more significant effect. All right? Because it's right where the positive charge is. But the way I put it, the positive charge, if it comes from the other ring, has to skip it. So it's only a minor effect, not a significant effect.
Oh, okay, got it. Thank you.
Okay. The black dots are where the positive charge can reach in resonance structures. Okay, I used that once before for one of these sessions. It's a shortcut. So if you finish the top structure, and you can use the shortcut too, as long as you're sure. Okay, the top structure, the black dots show everywhere the positive charge can reach through resonance. And it always alternates this way. But it can only go to the right-hand ring in the way I just showed. Okay. Rita, is that how you pronounce it? Rashad? Rashid?
Yeah, Rita. So I'm still trying to figure out, like, I don't know why I'm not understanding, like, the phenyl group, like, how activating is it compared to, like,
Well,
an amine group? Is it more activating than an amine group?
If it weren't for the fact that the hydrogens here are a little bit in each other's way, it'd probably be a strong activating group. But that diminishes how much it can activate it. So it's about like an alkyl group in general.
Okay.
Okay, so it's just a weakly activating group, right?
Okay.
It's capable of being a strongly activating group, but it's got a problem. So it ends up weakly activating.
Okay. That makes sense. Because, like, I have, like, the list that I found on Google that has all of, like, it compares them, but phenyl isn't on that list, so that's why.
Yeah, it's often avoided because of the complications, but I love to put it on these biphenyls so students can pick the right ring. That's the main point of it.
Right. Yeah.
Yeah, I mean, it's going to go on the, it's not going to go where the meta director is, because that's the less reactive ring. Meta directing means deactivating, means, hey, other ring. That's the major point here.
Right. So, like, with E, the only reason that it was on the ring with the NH2 was because of the H2SO4.
E. Oh yeah, the sulfuric acid changes the amino group. I think I referred to this in both sections. The amino group is like Dr. Jekyll, Mr. Hyde. It can change its character very quickly. I assume everybody knows the story of Jekyll and Hyde. It's a classic age-old story. If not, check it out.
Yeah, I don't know about that, but I'll look it up.
Yeah, there's been at least a half a dozen movies made about that story. It's that common. It's just about a doctor, a well-respected doctor who starts playing with things he shouldn't play with, and he treats himself, and all of a sudden he starts kind of spontaneously turning into this evil Mr. Hyde. And he goes back and forth. And it, makes for an interesting movie, but it's a classic story of the good and bad in all of us. Is the underlying meaning. We all have a bad side. We all have a good side. Somebody wanted to know about the other ones. Who was that? B and E. Oh yeah, reading the novel is always better, but the movie's faster. Okay, yeah, B we did. That's kind of what we're talking about. E. Yeah, E we've talked about, it's the protonation. I think you've caught all that by now, whoever it was that asked that. That was Alexandra. So you cool with all that?
Professor,
Yeah.
for I'm doing the homework for chapter 20, for 19, sorry. And I'm doing 7A. Why don't we lose water under basic condition? Like why do we only get the acetal in acidic conditions?
I think there's a numbering inconsistency between the assignment and the answer key.
Okay, so we
Nobody has
react.
complained about it yet because you're not turning that one in. I gotta work that out before I issue this again. Let me pull up the original assignment. Yeah, I don't know how that happened, but
No, it's the same.
okay. Well, at some point there is a numbering difference. I think there's some things missing from the key. Which question are we talking about? 8?
7A. Why don't we
7A.
like we've emphasized in the book that you get acetals in acidic conditions. So why do we stop at the hemiacetal in basic conditions? Is water not at all? Is there no source of proton?
There is a slide specifically on that. Let me find it. Sorry, I should be able to find it faster. I missed it. Must be earlier. Here it is. Okay, back up a little bit. Here's the full mechanism for making the acetal an acid. And one of the key steps is the structure right in the middle here.
Right.
You have water as a leaving group and the lone pair helps. So you have a positive charge, you get a positive charge. It all looks okay. But if you try this with base, the alkoxide, methoxide, the alkoxide will add, you get the anion, you can quench that. But now you have to lose hydroxide. And what's going to help you do that? And the answer is there's no way to do it.
Okay, so you're assuming there's not enough of an aqueous environment for water to act. Like
no, you can't protonate something in the presence of hydroxide.
Okay.
If you're an acid, if you're doing an acid mechanism, you're an acid. If you're doing a base mechanism, you're in base.
All right, thank you.
You can't just use acid or base, whatever works for the next step. That's
right.
A very, very common mistake.
Because I was just doing it and I was thinking, well, where are we going to get the proton? And I was like, oh, well, maybe there's water. But
yeah, well, even if you had a lot of water there, we have the self-ionization of water, the equilibrium constants 10 to the minus 14th. You do the math, you have so little H plus, it can't do anything.
Okay.
At some point, the amount of H plus gets so small, even though we can calculate it, it's not enough to do anything.
Fair enough. Thank you very much.
Yeah, it makes me remember any strong acid will protonate an aniline. Yes, Robert. It makes me remember the compound I worked with in industry for a couple decades, actually. I worked with it for a long time. It shreds DNA. You can show in a test tube that it can grossly damage DNA at femtomolar concentrations. All of a sudden, a rumor was going on, hey, one molecule of that stuff can kill you. No, that's absurd. If one molecule could kill you, I wouldn't be around.
Right.
Right? Because I'm sure I got exposed to that much. Okay, I have some hands up here. Are they old hands? Put your hand down if you've already asked your question. Robert, that was your question?
Could I ask something else?
Yeah, sure.
Okay. So I'm kind of confused about when we should indicate when a product should be recrystallized. So for example, in the homework in 6A,
Yeah, I'm not going to make a big deal out of that. Okay. Unless somehow I say, how are you going to make this pure? You don't need to worry about it.
okay, so
If I say the word pure, then you got to worry about it, right?
okay, so
That
for
would be
6, when you add the methyl group, because in this case we need it to be para to get our product, should we just include the para addition?
Okay, well, there are complications because not everything is crystalline. Doing recrystallizations at -78 is possible, but very challenging. You need the right equipment. So in 6A, aniline's a liquid. This amide, if I'm not mistaken, would be a solid. You'd probably recrystallize. It'd be easy to do. It wouldn't take you much time. You methylate it, I don't know. That's probably still a solid. So you'd recrystallize it. But this methyl aniline, the toluidine, I think that's a liquid. So, you know, you got a practical concern with what you actually are going to have that's a solid.
Okay, so just to clarify, in this case, because the methyl group can add ortho or para, right?
Yeah, you'd want to recrystallize at this point, if you could.
On the exam, I wouldn't have to indicate that. I would just draw the para product, even though
if I asked you how to make this specific compound pure, then I want you to recrystallize it. If I say, show me a synthesis, no.
Okay.
And if you put the note recrystallize, it'll never hurt you.
Okay. Okay. So if you say pure, then write recrystallize.
Yeah, there's an implication there, right? If I say make it pure, don't show me the major product. Show me how to make the major product pure.
Okay. All right. And if you don't ask for that, even in this case, when we have both ortho and para products, I can just put the para product.
Yeah, you know, I like it when students say I'd recrystallize it, but in the real world, you recrystallize everything you can.
Okay. All right. Got it.
And by the way, if this toluidine, I'm calling it this paramethyl aniline, if it's not a solid, you make a salt. You recrystallize the salt. Then you unmake the salt.
Okay.
So, yeah.
All right. Thank you.
But when you take something that's not pure and take it on to another step, and now you make impurities out of your impurities, life gets more and more complicated. It's higher risk work. When you're doing this the first time, you just purify everything, unless the NMR says, hey, it's good stuff. So I'm going to put down some hands here, but raise your hand again if you have a new question. Okay, Cam, you had a question?
Yeah. So in lecture, I think you mentioned that for both aldehydes and ketones, they're hemiacetals. The major product is still the aldehyde or ketone, but the textbook says that for simple aldehydes, the major product is largely the hemiacetal or the acetal. Could you go over where the equilibrium lies again?
If you throw a little aldehyde and a whole lot of methanol, then I believe them. If you have a lot of aldehyde and not that much methanol, then I think it probably prefers the aldehyde. But, you know, I'm not going to argue about it. It's an equilibrium. There's quite a bit of both.
Okay.
For the ketone, there's definitely significantly less.
Got it. Thanks.
Alexandra, you re-raised your hand?
Yes, so I have two questions on.
Sorry to put your hand down.
Oh, it's okay. I had two questions. One kind of goes off of what Robert was just saying. So for the recrystallization step, we would just write like an arrow that says recrystallize.
Yeah, you can do it that way. You know, it's a real step. It's not something you do on the side.
Okay, and then my other question is how, like, I know we do acylation or acylation when we don't want the nitrogen to react. So just, I guess my question is like, how exactly do we know when we need to do
If you're
acylation?
doing anything to an aniline and you unless you want it protonated, I would acylate it every single time.
Okay.
You're much more likely to be happy with the results. And I'll never count it wrong if you do that to tame the aniline.
Okay. Thank you.
Yeah, and you don't have to worry about experimental details to make the amide or to hydrolyze the amide. I mean, you can write the word acylate and write the word hydrolyze. I'll be happy on this exam.
Okay, and I guess I also have one more question is on the aldehydes and ketones
Sure.
homework with the naming.
Uh-huh.
So I think it was the aldol, and then the one like right under it where you wrote the butyric. I was just a bit confused about the common names, like why one was beta and one was delta in the answer key. So like the aldol was beta
Do I have the answer
hydroxybutanol.
key open here? Yeah, there's the key.
Right. So I thought for this one that the butyraldehyde would be gamma.
That is gamma. My bad.
Okay, thank you.
Thank you. You should have sent me an email on it. I'd have apologized sooner.
No worries.
Never assume I can't make a typo or an overt mistake for that matter.
Wait, can I just ask them something along with her question then?
Absolutely. Is it Eileen?
Yeah, Eileen. So I also thought it was gamma. So I was really confused when I saw the answer key. So I just wanted to make sure. So for alpha, beta, and gamma, like it's just how many like positions it is away from the carbonyl carbon,
Yeah.
right?
The only thing that confuses students is when you number it, the one up here is numbered also. 1, 2, 3 hydroxy, but alpha beta hydroxy. They're offset. They start at a different place. That's the only tricky thing.
Okay, so you would also count so the oxygen would be gamma position, right? Like for the common name question.
At the bottom?
Yeah.
Yeah. Alpha, beta, gamma. But if you were to number it, it'd be 1, 2, 3, 4.
Okay. I got it. Thank you.
Yeah. And again, the alpha and beta, I might go real easy on that, but you're going to see it all over biochem. Alpha amino acids, anybody? That's the meaning, alpha amino acids. So there's a good way to remember which one alpha is. If you know what an alpha amino acid structure is, the basic structure.
Wait, I have another question for that.
Sure.
Question. So we don't count the oxygen, right? It's just the carbons. So
yeah,
like
we only number carbon chains.
Okay, so the oxygen is attached to the gamma carbon. So that's why it's gamma.
Yeah, alpha, beta. Yeah, the gamma says what carbon is it on.
Oh, okay, I got it.
That's just like the number. Okay, again, if you ask a question and you're done, put your own hand down. Avoid confusion. Rita, you had your hand up?
Yeah, I had like kind of an unrelated question.
That's fine.
You were saying that we can redo the homeworks until the test day. Does that also?
Yeah, if you submit them the same day as the exam, I'll accept them. If you submit them the next day and I don't notice, I'll accept it. But I don't want them turned in forever.
Yeah, because like I never did the like the corrections because I didn't realize that we had to do that to get full credit. So like for the ones that you already graded, can I do the corrections for those and then?
Yeah, send me an email, will you?
Okay. Okay, yeah, because I'm just like 1 point away from like an A, so I was like,
oh my.
so yeah. So I'm gonna do the corrections and I'll email you.
Well, email me first. So we'll see whether, we'll see.
Okay, I'll email you. Thank you.
And for Rita and everyone else, doing your homework is preparing for the exam, but don't spend so much time trying to catch up on old homework and don't get ready for the current exam. Okay, it'd be a mistake. The exams count a lot more. Make sure you get a good score on exam 3. I'm more forgiving on the homework.
Yeah, like the thing is I already did, like I always look over the questions anyways and like make corrections. I just didn't like take pictures and submit them.
Sure. Yeah, you're probably not the only one. By the way, on a question like 2, I don't expect comprehensive answers. I expect answers that indicated that you tried to find them and considered various possibilities, okay? It's a pain in the butt. And I'm not guaranteeing what I have is comprehensive. On the other homework, there was one, and I missed one of them, you know, an obvious one. I missed the benzylamine. I was looking for fancier ones. So these questions are to help you with your mental flexibility when it comes to structural possibilities and clearly seeing the structural possibilities. So they're, if these things are hard for you, you're the ones they're meant for. I don't know who was first. Olivia?
Yeah. Hi, Professor. So I was looking at the chapter 19 aromatic substitution homework. And then for question 6, part E, I had like a particular question for that.
What was your first question?
So it's particularly like it's question 6, part E.
Okay.
And so I just wanted to ask, just generally, this is also a general question in the sense that, does the addition of the methyl group have to be before you convert it to the diazonium ion? Or can you do it in the reverse order?
You could make the phenol first. First off, let's go back to the very first step, the way I have it. You have to acylate here now or you'll methylate the aniline.
Right.
Okay, so you could make this into phenol and then you could make an ester out of phenol and methylate that. So that would work. Methylating the phenol would risk making the ether.
Okay. So doing it in that particular order would probably be the easiest way to do this.
Probably, but you know, you show me 20 steps, you get it right, I'll give you full credit. You're just gonna be in the lab a lot longer.
Fair enough. Okay. Thank you.
Sure. In graduate school, you might have an exam question that says, show me the shortest route to, but not on my exams. Madison?
Hi, Professor. I have a question about the ketones and aldehydes homework. It sort of overlaps with the mechanisms of question 8 and 9.
Okay.
I was just wondering, under what situations would we use the lone pair on the oxygen to make a pi bond? Would it just be to force out the water as a leaving group?
Well, yeah, this structure right here that I'm circling.
Yes.
Yeah, you may show this as just the loss of water and put the positive charge on carbon. I would not mark it wrong. You've just shown a different resonance structure than the oxonium cation. In general, we tend to show the most stable resonance structure. So that's what I do. But if you just left the positive charge on the carbon, that wouldn't be incorrect. I would just hope that, hey, I hope you realize that's oxygen stabilized. Okay?
Okay, thank you so much.
Yeah, so, you know, that lone pair is helping whether you actually show it or not. It greatly stabilizes the resultant cation. Jackie, you have another question? I think you've been waiting.
Yeah, I did. I'm just doing the aldehyde and ketone homework here so that I can ask questions as I do it.
Oh, I hope
but
I'm not giving away too many answers.
no. I mean, I'm doing it without looking at the answer key, and then I'm checking my answer.
Sure.
And number 7B, I'm still on question 7. We only get the hemiacetal because there's not enough heat. Like we don't proceed.
Yeah. I mean, what's intended here is you answer B and C as a pair of questions.
Right. So when we distill the azeotrope is our ketone and hemiacetal mixture.
No. These things are generally done with an excess of an alcoholic solvent, whatever you're making the acetal out. Most commonly methanol, sometimes ethanol, and they both azeotrope water.
So so when you're saying distill the azeotrope, we're getting rid of the water.
Yeah, you're slowly distilling out methanol, and it takes water with it.
Okay, so
and
that
so
means
you want to distill it at a rate that's comparable to the reaction. If you distilled it too fast, yeah, you'd be losing too much solvent too fast.
So that's how we force it to the acetal.
Yeah, and as I said, there are chemical ways to remove the water too when you need to.
Right.
But distillation is cheap.
Okay, so we're removing water.
Yeah,
so
we're removing water via the azeotrope.
So because otherwise this reaction isn't really that favored, right? Because we're a ketone.
I make an assumption that students have someplace learned what an azeotrope is, or they're going to look it up.
No, I looked it up, but I wasn't sure what the two liquids we were distilling, like, because azeotrope is two liquids at the same time.
The idea is get rid of the water, and alcohols in general azeotrope with water.
Okay.
And I mentioned in one of my lectures, but probably not the other one, the other section, if you take 95% ethanol in water, if you put this on your tongue, it burns a little bit. I've done it. It's about as strong as you want. If you take that 95% alcohol and distill it in the world's best still by the most careful method, you still have 95% ethanol.
Right.
For some strange reason, the mixture is the lowest boiling thing. And I've never understood that. I've always wanted to, but it's just a strange phenomena. And you get ternary azeotropes too, where 3 things will co-distill.
Thank you very much.
Okay, Ahmed, Abzal.
Yeah.
However it's pronounced.
It's Abzal.
Abzal.
Yes.
Got to put the emphasis in the right syllable.
So I have 2 questions now. Going on the same thread of number 7, would it also be possible for C to get an elimination reaction as a byproduct?
That kind of thing can be done, but you'd need different conditions. You couldn't do that in methanol. In methanol, you'd add methanol back.
Okay, I see. And then for number 8.
But that's a good question, actually. Number 8.
Yeah. So where after the carbonyl is protonated, could a methanol attack that, or does the intermolecular reaction have to happen?
A student put that on their homework, and when I self-corrected, they asked me about that. The intramolecular is highly favored.
Okay, I see.
So adding the methanol first is certainly a theoretical possibility, and if you did it correctly, I'd give you an awful lot of credit on an exam. but it's hard to fight the entropy. That OH, one way to do this, in fact, you can actually calculate based on the rate, the apparent local concentration of this OH group. And it's very high. You know, it's a fancy treatment of it, but you know, it acts as if it's in a very concentrated solution of this OH, not the methanol.
I see. Yeah, that makes sense.
Yeah, so it's an entropy thing.
Okay, thank you.
Yeah, Olivia, you had another question?
Realize I never put my hand down. My bad.
That's okay. That's okay. KM, did you have another question?
Yeah, it's about naming aldehydes in this homework.
Right up here.
So for the butyraldehyde, is that the common name, and is butanal the IUPAC name?
Yeah, I mean, I'm not going to put this on the exam, but you know, it's acetic acid, propionic acid, butyric acid. You need to know that after, well, the next chapter.
Okay. And
so here I actually told you the C4 acid is butyric, so you could derive butyraldehyde.
And that's the common name?
Yeah, butyric acid is the common name.
Okay.
And when you hear that name, you should think stink. I'll speak to that in the next chapter.
All right.
Alexandra.
On number 7 of this homework, for part H, would there be syn and anti for this one? Anti?
7H, absolutely. And as long as you're aware that they exist, that's all I care. I mean, it's not a big problem at this level.
Okay, so like we shouldn't worry about like
No,
preferring
you shouldn't worry showing those as a product.
Okay.
You know, if I want to address that, I'll ask a specific question on it. And
okay,
you can't isolate them anyway. They interconvert. So, you know, unless I focus on it, what's the point?
Okay.
By syn and anti, do you mean E and C for H?
For H, the OH can be written on the right or on the left.
Right. Okay. Yeah.
They're technically separate isomers, but they can't be isolated and put in a bottle. In many ways, if we can't separate them and put them in different bottles and keep them that way, we kind of consider them the same compound. But you will see these in the NMR. You'll see the two forms. So they're, yeah, it's kind of worth mentioning. Yeah, so there's actually 3 compounds on here that would exist that way. More questions? We've only been going for an hour. That's not very long. Of course, we didn't get that many people either.
I have a question.
Okay.
Regarding
Vinny?
this part, yes, regarding this part of the homework.
Uh-huh.
So when they ask for catalyzed hydronium or like catalyzed acetic acid, I'm confused to us when does the hydrogen adds to the ketone?
Well, if you have a weak nucleophile, a ketone has to be protonated before it can react.
So, okay, for number for J,
J.
I'm assuming that we add the methyl. I'm confused too when we add the hydrogen to the.
Okay. Cyanide is a good nucleophile.
Oh, for J.
Huh? Sorry?
For number J?
J. Oh, J.
Yeah.
Okay. An amine is kind of on the cusp, kind of on the borderline. So, you know, if you show the oxygen protonating first and then the nitrogen coming in, I wouldn't worry about it. But the nitrogen is able to attack without protonation. It's just barely good enough.
Okay, because what I was thinking was I did the protonated amine first.
Well, no, you can't have the amine protonated and have it still act as a nucleophile. You just took away the lone pair.
But then if you, because what I was thinking that if you took away the hydrogen from acetic acid, wouldn't you like produce a base?
Acetate is indeed a base, but not a very good one.
So, okay.
Yeah.
That's the thing I'm confused about. So no strong base can be present, but weak base can be present.
I mean, you can call chloride a weak base, or maybe we should call it a really, really, really wimpy base.
That's why I was confused.
Just remember that acid and base is always relative. George Olah showed that methane can serve as a base if it has no choice and the proton wants to go someplace. So acid and base is always relative.
So for example, for D.
D, yeah.
For the same question, D, I did protonated hydrazine.
Okay, now you don't want to protonate your nucleophile. Maybe this will help. Let's go back to J. It's a little easier. The hydrazine is more of a special case. You know, I put catalytic acid in there, but in practice, you don't really even need it. It's just such a good reaction. For J, you've got a little bit of acid in with methylamine and a ketone. So what's going to get protonated? The methylamine. But that doesn't mean that you can't protonate just a tiny bit of the ketone at some point. You get this good collision, the proton ends up on the ketone, okay? It may only be 1 part per million, but proton exchanges are very rapid. And a little bit of protonation can win the day.
So for J, we would, I'm confused as to if do we do protonated ketone or do we do protonated amine?
You do not want to protonate the amine. It can't be a nucleophile.
Okay.
But some of the amine would be protonated. You really have a mixture.
But if you protonate amine, right, the oxygen can still take away the hydrogen from the amine. But it's just...
Well, okay, let me bring up ChemDraw here. With my ChemDraw. There it is.
Because my thinking was, if I have a protonated amine, the ketone can still take away the hydrogen from the protonated amine.
Okay.
And I'm so confused.
That's okay. It's getting unconfused where the learning happens. Okay?
Yeah, it's just whenever there's a catalyst present, I don't know what the step happened.
Okay, well, it's complicated here because of the presence of the amine. So this is a little more complicated situation. So in the reaction flask, you're probably going to have these species. Okay? You're going to have the ketone, you're going to have some free amine, you're going to have some protonated amine. Okay? So the simplest way to do it is just to let the lone pair on the free amine attack. Okay, it does have a little tiny lone pair. I don't know why they make that so small, but that lone pair can attack. you can get a species now that has charge separation, so that's a strike against it. You know, and knowing where the borderline is important, and that's probably the amine. Sorry, this isn't faster. Okay, so that is an acceptable intermediate. Okay? But another choice is to have a less likely event. This thing has. Okay, there, it's pointing at the hydrogen. I'm going to be lazy. It's also acceptable in my mind anyway. Oops. Oh. Yeah, I'll open it that way. It's also acceptable to protonate it first. Now you got to realize that the vast majority of protons are going to be on nitrogen, but that doesn't mean a proton can't go on the ketone just every now and then. And the first thing it's going to think is, what am I doing here? But before it can leave, the amine can attack. Okay.
Okay, that.
So I would on this specific question, I would accept either nucleophilic attack followed by protonation or protonation followed by nucleophilic attack. I accept either order.
Okay. For H, I did the same thing as protonated ammonium.
Okay, well, H and D, I would say, are different because they're much better nucleophiles. It's about the alpha effect. The nitrogen and the oxygen of the hydroxyamine that used here up in the reagents, wherever it is, the hydroxyamine, that nitrogen is unusually nucleophilic. So I'd still give credit when I list the acetic acid here. I still give credit for protonating first, but here it'd be better to show the nitrogen attacking first. And the same thing with the hydrazine. It's unusually nucleophilic. Where's the hydrazine? D. Yeah, I've shown the catalytic acid. So if you want to use it, protonate the carbonyl first, please do so.
But the thing is, for me, I was thinking if I was thinking of nucleophilic attack first, and then protonation of acetic acid, but then it will produce a base, which doesn't make. I think the strong acid.
Yeah, I hear you. You know, if you feel more comfortable protonating it first, fine. I consider that acceptable.
Okay, that makes sense.
Yeah,
thank you.
And if the amine attacks first to make O minus, that O minus is not going to be there long enough. Okay, so it's a borderline case.
Okay.
So whichever you're more comfortable showing, whichever confuses you the least.
So it would still be acceptable if I protonate a nucleophile.
If I show an acid catalyst, you can use it first to protonate the carbonyl group. Yeah. The hydrazine and the hydroxylamine actually work without any acid catalyst added. It's just a very favorable reaction. It manages to get it done. It's just easier to think about a mechanism with the acid.
So for J, we're in acid, but we have a nucleophilic nitrogen.
Well, it's only catalytic acid. So you got free nitrogen at the same time. So
then I attacked with the nucleophile first.
Yeah, that's fine. That's acceptable.
Okay. And I find that the nitrogen nucleophiles, we usually attack first.
Yeah. So,
and then the oxygen nucleophiles, we usually protonate first.
Yeah, maybe this will help. If you mix diethyl ether with methyl iodide, nothing happens. If you mix dimethylamine with methyl iodide, you quickly methylate it. The big difference between the nucleophilicity of an oxygen and the nucleophilicity of a nitrogen.
Well, because the nitrogen's bigger.
Well, no, the nitrogen has a lone pair that's much more available.
Yep. Yeah. Never mind. That's fine.
Just to build off of this past question. So for catalysts, there's a difference between what is the exact difference between using a basic catalyst and acidic catalyst?
Well, it determines the mechanism.
Okay.
You know, you can't show the same mechanisms under overtly acidic conditions and overtly basic conditions.
Oh yeah, yes, you're right. Okay, yes, that rings a bell. Thank you.
Yeah, students try it. They never get full credit.
Professor?
Yeah.
Yeah, just to kind of stick with the conversation that's been going on. That doesn't that sort of also kind of dictate whether or not we would first protonate the carbonyl oxygen, for instance, like whether we're in like overtly basic or acidic conditions. Like if it's much more acidic conditions, your first step would more likely be.
Well, again, if you only have catalytic acid, then you have free amine available. And that begs the question is, does the amine need the help? Is it going to wait for the help?
Mm-hmm.
So that's how you should think about it.
Okay.
So
And
here, you know, I'll go either way.
Yeah, I came in unfortunately a little late. I was wondering, I hope this isn't redundant, but just with the first three, A, B, and C, I just wanted to like disambiguate between them a little bit, if you don't mind.
Yeah.
It looks to me like A and B are kind of like nucleophilic addition in basic and acidic conditions, respectively.
Yeah, they give the same product too.
Yeah, and then with C, the technical language there of refluxing and slowly distilling, we're kind of talking there about like removing water, right?
Yeah, yep.
And
Methanol
so
azeotrope with water. It's not quite as good as ethanol for azeotroping it, but it sure gets the job done.
so that's all by way of saying like we're removing water and we're doing acetal form. We're favoring acetal formation because we're taking water, which is a product out of the vessel and pushing it towards the product because of Le Chatelier's principle.
And this is not just a way to imply that's happening, it's how it's actually done.
Okay, great, thank you.
You actually can do reactions in solvents other than alcohols, like benzene, and distill. And in that case, the water will separate in your receiving flask. So you'll get a benzene with some water floating on it or floating under it. The benzene will float on the water.
Gotcha.
Professor, can I ask why B doesn't make the acetal or the acetyl?
Well, again, in this, you know, I like to say everything depends on context, and that's absolutely true. In the real world as well. So B and C are a pair. So what's the difference between them and what's going to happen? I don't think you can make an acetal at room temperature. It would be very slow, but you know, I don't expect you guys to know that per se. So I've paired these up so you can figure that out.
So at room temperature, then should we just stop at the hemiacetal?
Yeah, you gotta reflux, you gotta remove water. If you don't have a step for removing water, the best you can hope for is equilibrium.
Okay, so just as a general rule then, at room temperature, we stop at the hemiacetal.
Yeah, to make an acetal, you gotta remove water somehow.
I mean, what I did in my mechanism was I had an OH group and I just had that protonated by H2SO4.
Oh yeah, no, you can draw a mechanism at room temperature, but that doesn't mean it'll go. But again, this is intended to be a pair, so what's the difference?
One has reflux.
Yeah. Yeah, well, no, the big difference is you're removing water. That's the hint.
Okay, I was kind of confused. I mean, because I sort of understand from what I understand, an azeotrope is a mixture that has two very close boiling points. So
No, it's not that simple. It's a complicated phenomena that I've never fully understood. Things do azeotrope that have fairly different boiling points. It's not a lack of separation, it's an inability to separate by any technique. There is no distillation that can separate water and ethanol if you have 95% ethanol, even though the boiling points are 30 degrees different.
Okay, but the key in C is that by distilling the azeotrope, you're removing water, which allows you to make the acetal. Okay, all right, thank you.
Yeah, I mean, C, if I wanted to be picky and didn't put down the azeotrope, the correct answer would be a mixture of the acetal and the hemiacetal. But no, I'm not going to go there. I'm going to have it clearly one or the other, I hope.
All right, got it. Thank you.
I have a really random question.
Oh, great. Random questions are usually the most interesting.
It's not really that interesting. It's just I keep forgetting. So if we have a benzene, if we have a phenyl group on, and so if we have aniline or phenol, how does that affect boiling point? Does it bring it down or bring it up? Like
the OH?
No, the phenyl group. So.
Oh yeah, well we've talked about that.
I know, and I forgot, and I just, instead of sifting, I might as well.
No, that's okay. I don't mind. Okay, so there's phenol itself. Anilines, I assume, have similar trends, but I actually don't know a rule for that. The anilines hydrogen bond a little better than amines because the nitrogen is more electron poor from the ring. Okay, so I haven't gone into anilines. Aniline itself is pretty high boiling and it's kind of oily. But phenol, this ring is much more polarizable. And that makes it act like more carbons. So the rule of thumb is it acts like 6 carbons for boiling point. Instead, I mean, 8 carbons, I'm sorry, 2 more. It's 6 carbons and it acts like 8 carbons for boiling point.
And for solubility?
Okay, the solubility, the polarizability now helps the solubility. And so it acts like 4 carbons.
Okay, so basically these rings will make, they increase polarizability and the charge is distributed. So the boiling point goes up and the solubility in water goes up.
Yeah, and it's the same thing for benzene itself. Benzene itself has a much higher boiling point than cyclohexane.
Right, okay.
And it's for the same reason, but what is the name of that force? You've still got to call it a London dispersion force, it's just a better one. Okay. It's still an induced dipole that we're talking about here.
Thank you.
And none of that has anything to do with the fact that the ring is planar and makes it, for instance, more available for hydrogen bonding?
You can't hydrogen bond to the ring. I mean, the oxygen's more exposed?
The OH groups are like less.
That's not a major factor, the steric hindrance. I mean, T-butanol hydrogen bonds in water just fine. It's miscible in water.
Gotcha.
Yeah, of the 4 butanols, T-butanol is the only one miscible. So that argues against any steric hindrance being a factor.
I'm sorry, can we go back to 7J, for example? I think you have it on this chem draw right now.
That was the one that was on chem draw.
Yeah, I don't really understand the role of the catalyst. So it can protonate either the carbonyl group or the methylamine.
Oh, it's going to protonate the methylamine much better. I mean, a carbonyl group sucks as a base. Forgive my language. A nitrogen's a real base. So if you put a little acetic acid in here, the proton all goes to amine first. Okay, but the ammonium salt, however poorly it can do it, can occasionally protonate the oxygen. It's It's quite a bit uphill. It's not very favorable, but you know, I'm not going to preclude it.
Okay.
But certainly this alkoxide is going to protonate like a shot.
So in general, the catalyst is used to protonate the reagent, not the carbonyl.
Yeah, if there's a catalyst in there for the purposes of this class, you can assume that it can activate the carbonyl so that a weaker nucleophile can add. But I can't explore the details of every single possibility, so I've never explored this. But I've always had the impression that amines can add without an acid.
I'm sorry, when you say activate the carbonyl, do you mean protonate?
Protonating it is activating the carbonyl. It's making it much, much more reactive.
Okay, so the catalyst serves to protonate the carbonyl or the other reagent, or both?
Yeah, well, you have to make a choice if you're going to write this down.
Okay, so
the way I showed it is the nitrogen will attack first, then it gets protonated.
In the book, they very specifically, I'm sorry to butt in, but if it helps, like it's been helping me, is the nitrogen nucleophiles attack first, and the oxygen nucleophiles in acid, the carbonyl group is protonated first.
Yeah, that's the way I would prefer you do it.
So the attack happens before the protonation.
Yeah, I think that's the better way to show it.
Okay, another thing that's kind of confusing me is when you make that attack, you have a negative charge on the oxygen, but you're in acidic conditions. So
yeah, but it's very transient. Remember in the Wolff-Kishner reaction, we're in alcohol and we make a carbon anion.
Okay.
Which is just as incompatible. So transient species can be generated. It's just a question of what it takes. So an amine can do this, an alcohol can't.
Okay.
You have to have enough driving force to make that.
Okay. Okay, got it. Thank you.
Yeah. So yeah, because it gets a little bit confusing, I don't mind if you show up protonating first, and it may depend on it. If you put 90.95 equivalent of acetic acid in there, hey, maybe you're going to get a lot of protonation first. You know, not all mechanisms are single mechanisms. There can be more than one thing going on at a time. Most textbooks teach you to think, oh, this happens and that happens, I'm done. You know, I try not to make it that simple because it isn't. But if you want to take the simple approach, certainly, I'll give you credit.
Professor, I have a question about the acidity of amines.
Yes.
You
mean the acidity of ammonium salts or the conjugate acids of amines?
A conjugate acid of amines.
Yeah, same thing. I said the same thing twice. Okay.
So I would think that a tertiary amine, well, the conjugate acid of a tertiary amine would have a higher pKa because if the groups were all methyls, they would make it harder for the amine to, they would put a larger positive charge on the amine than something like a ammonium ion. But the textbook gave a table that didn't really.
This is something I really didn't cover. You know, we're not doing the amine chapter proper. You got to make some compromises and you teach Orgo because there's way too much to teach. But tertiary amines are actually slightly better bases on average than primary or secondary amines. So the protonated form is more stable. And you can think about it as the alkyl groups being electron donating and helping to stabilize the positive nitrogen to some extent.
Okay.
And when you go from primary to secondary to tertiary amine, there's a tendency to get more nucleophilic. So they get a little bit more reactive. It's not a big effect, so I can justify skipping it. But if you see it in the book, that's what it is.
Okay. I have another question about a mechanism.
Sure.
In the slide where you talk about acetals as protecting groups for alcohols.
Yeah. That's the
I was
way
trying to
it is.
work that.
You have a slide number?
No, I don't have the numbers. Towards the end though.
Okay,
184.
184. Okay, this is kind of a special case. Okay. So
I was wondering how you would start the mechanism to create that complex.
what are the possibilities? It's acid catalyzed, so go ahead and use the acid first.
I would protonate the oxygen on the ring.
On the ring. Okay, that may happen. Is there a better place to protonate than on the oxygen with the same compound?
Oh, the alkene?
Yeah. If you protonate the oxygen, you have an oxonium ion that happens to have a double bond next to it that's not going to help. If you protonate here where I'm pointing, you get a positive charge that is also stabilized by the oxygen. So the best cation from here is stabilizing the other end of, is protonating the other end of the alkene. And that's how you start the mechanism.
Okay.
And that takes you the product you want too, right?
Yep.
If you protonate the oxygen, you have no resonance structures and you haven't increased the reactivity of the neighboring carbon.
I see.
Okay. It's not that it can't happen, it just doesn't do any good.
Yeah, that's what I was kind of stuck on. Like, where do I go from here? I guess.
Yeah.
We don't.
Yeah. Again, you mix the other two starting materials and throw in your toluene sulfonic acid. It's going to protonate the first oxygen it runs into. It hasn't made a choice yet. But the most basic thing in this mixture is that carbon. Believe it or not. Because it makes them the most stable cation. Jackie.
Still on question 7. I'm on the last one. L.
Do I have to keep online until you finish the homework?
No, I'm doing the ones that are this one I felt like had a lot of nuances. So
yeah, there are a lot of nuances behind it, but this is supposed to be rapid fire. You got to know your products.
Well, I'm practicing my mechanisms though.
That's as good a place as any.
So for L, for what is this sodium cyanoboro like?
That reduces the intermediate cation. There's slides that show the mechanism on that.
Oh, okay. All right. So that reduces
that's reductive alkylation.
Okay.
Which one is that? L. Okay, yeah. So you're putting the amine there where the carbonyl used to be. It's a reductive amination with respect to the ketone.
Okay.
Okay, so that's a multi-step mechanism.
Okay, thank you.
But it's the protonated imine where you have the double bond between carbon and nitrogen that has to be reduced. It can't reduce it unless it's protonated.
Oh, I didn't realize that. So
yep. This is the wimp of all hydrides. It only protonates protonated species. I mean, it only transfers hydride to protonated species.
Okay, so this is a reducing agent for the protonated amine. I just have to review it.
Protonated imine with an I.
Yeah, IMINE.
Yeah, just to make sure.
So I just have to review that slide then, because I forgot about that one.
Sure. I don't know if you guys remember the calicheamycin from the functional group homework. We had to circle functional groups. It was the last compound that I think I noted as a particular challenge because there's functional groups there you don't know. If you remember that structure, I did reductive alkylations on that.
Can we talk about the reductive alkylation? Does anyone else?
Absolutely. on, go away. Um, You'd think I know the order of my own slides. Problem is there are two halves. Here we go. Okay, here's where the mechanism is. Okay, so I'm doing this with the allylamine and benzaldehyde. And again, I'm showing the nitrogen attacking to give the O minus. And then this would be protonated first because you have catalytic acetic acid in here. I should put that on the slide someplace. This would be protonated first and then deprotonated, get the neutral compound, reprotonated on the oxygen, eliminate. And here's the species that would be reduced. And so you just show hydride transfer from the reagent if you had to show a mechanistic step here.
Oh, okay. So that way we can go from this imine to an amine.
Yep. Yeah, it's a way you can reduce the iminium salt. If you just take sodium borohydride and the isolated imine together, you don't get any reduction. You need the acid to protonate the imine.
Okay, very cute. Thank you.
You know, to help you remember that, let me actually draw it out. Something I probably should have on the slides. Say goodbye. Okay, so boron is more electropositive. Oops, not bromide. Hydrogen is more electronegative than boron. So these hydrogens have some degree of partial negative charge. Okay, so that's why it transfers hydride. And the BH3 is not an unreasonable compound, lack of octet notwithstanding. So what's the impact of the cyanide? Okay, so cyanide has a triple bond, meaning that carbon's sp, and it's got that electronegative nitrogen on it. So a cyanide is fairly strongly electron withdrawing. You know that from electrophilic aromatic substitution because that's a fairly strongly deactivating group. Okay, so that now you've put something electronegative on the boron, and it's going to make that boron a little bit more electron poor than it normally is. And as a result, the hydrogens are going to be less electron rich. So the effect of the cyanide is to make the boron, in effect, more electronegative and not give as much electron density to the hydrogen. So these hydrogens have a much smaller hydride character.
So it makes it a weak reducing.
It makes it much weaker.
Okay. And just so I'm hammering this into my mind, we have a protonated imine. We're in acid here, and we have this poor reducing agent. We end up with a protonated imine after a series of steps. Then we deliver the hydride to the carbon so that the pi bond between the formerly carbonyl carbon and the nitrogen goes back up, and we end up with an amine.
Amine.
Yeah, amine.
Yeah, we often change the emphasis to help verbal understanding. So it's an amine and an imine.
Okay. Thanks so much.
Okay, so here's the mechanism, that last step, just for the record. The hydride comes in, lone pair goes up, you're done. I mean the lone pair. It becomes a lone pair again. The pi bond sends the electrons back to the nitrogen to make a lone pair.
Professor, I actually have a good question that relates to this concept. It's on the homework, your answer key. It's on 16C.
Yeah, there is one typo on one of them, on the aldehyde and ketones again. 16.
C, yeah, you see how it's intermolecular formation of the imine?
Sure.
And then you're constantly reducing it?
Yeah.
Yeah, so the question I wanted to ask, I just want to make sure I'm getting this mechanism correctly. So you introduce your
Did I show this in the answer key? The answer key has some problems, I
no,
think.
you didn't show it. You just gave us the product.
Oh, okay. So the mechanism. Yeah, that's right. This wasn't a mechanism question.
Yeah. So you introduce the nitrogen group, then you reduce it, then you still have a secondary amine.
Yeah, it's 3 of the same mechanism we just talked about.
Yeah, so you just keep doing it over and over until all the ketones are gone, or you reduce it and all the waters are removed.
Which carbonyl group is going to react first?
The center one.
Nope. Aldehydes are more reactive.
Okay, you got me there.
Yep. But then, because of entropy, it'd probably make the 6-member ring before the other aldehyde got involved.
Oh, so would it react with the first aldehyde and the
It'd
second
react
aldehyde?
first with an aldehyde, then with a ketone, then the other aldehyde. So the first one is inherent reactivity that's winning. The second one is entropy that's winning.
Can you explain this entropy thing?
Yeah, I mean, so let me draw this the other side. So that's the first intermediate, right? And this nitrogen can make a 1, 2, 3, 4, hold it. Did I take off a carbon in doing that? Yeah, I did. Chem draw. Don't do that on your exam, guys. Don't lose carbons. Whoops. And so this is the first intermediate. I'm absolutely certain of that. And so the question is this going to find that carbon down there, which is a 6-member ring? Or is it going to somehow find this one? So that'd be a 6, 7, 8, 9, 10-member ring. So this chain is floppy. This chain is floppy. It's not going to find the 10-member ring.
Okay, so it's just the proximity.
Yeah, proximity. Yeah, entropy, proximity. It's kind of the same thing.
Entropy is the same as proximity. That's what you
In
want
this
to
case,
think of it like?
In this case, it's the same thing.
Okay.
It's, you can count, I don't know if you were here for the whole thing, but if you calculate the concentration of this primary amine in the vicinity of the ketone, it'd be much higher than calculating its concentration in the vicinity of the aldehyde. And they can do that kind of thing. Those aren't easy numbers to get, but you can do that. And so it has an artificially high concentration around the ketone versus the aldehyde.
All right, I have one more question on the homework answer key. It's on 10D.
What happened to question 7? I thought that we're all we're doing today.
Yeah, so 10D, to create the ester, is that a acetyl formation? Like not hemiacetal? Like what is happening there, Al?
10D?
So the third one.
Oh, there's no C here.
Yeah.
That's why I'm confused. Reduction of the ethyl ester. Yeah. I am in parentheses as chemistry you're not responsible for.
Oh.
And I'm showing synthesis of the methyl ester. Don't worry.
So that's not an aldehyde ketone reaction.
This is the reduction of an ester with dival to give an aldehyde.
Oh. Yeah, I saw these in the slide, but I know these are for the carboxylic reactions, but this, do we have to just know the general reaction, like reagents?
It's the reductions and oxidation here that are the important ones. Reduction of the nitrile, the ester, and the acid chloride are the ones that are the focus here.
So that's like a different, like that's a way to create create esters from carboxylic acids.
Yeah, methanol and a dehydration. So we'll get to that in the next chapter.
Okay.
Yeah. Just a little comment here. It may not be obvious. Most students would ignore it. And I don't mind if you ignore it. But if you reduce a carboxylic acid with LAH, in theory, you get the alcohol. In practice, you often get a mess. Because in the process of the first reduction, or even before that, you get all sorts of insoluble material. Insoluble material doesn't react very well. So LAH is not a good way to reduce acids in general. Borane is a great way. BH3 just as a reducing agent. So I just noted that parenthetically here. I'm not going to include that as part of the curriculum. Actually, I don't think it's in the next slides, in the next chapter. But it is one of the best ways to reduce carboxylic acids, just borane itself. I haven't been paying much attention to the chat.
Professor, can we go through the mechanism for 7K?
7. Oh yeah, that was kind of a, let's see if they can figure this one out. Okay, yeah, I do that too on homework. I do it less on exams. If you just go through the mechanism for the imine formation. So you can do that, right? So I'm assuming you can make an imine here. Okay, the nitrogen attacks. You move protons around, you lose water, you end up here. Okay, so how do you make a neutral compound out of that? Well, the trick is, oops, that's not what I teach. You got dimethylamine in here. And so it's simply this type of deprotonation. Okay, you've managed to lose a proton.
I have a question because I was just doing this question. Can we use acetate to deprotonate the compound?
Well, if you have a competition between an amine and acetate, the amine is the better base. It's the one you should use.
Okay, because when I was drawing this, because I saw that acetic acid can be deprotonated and protonated again. So I was thinking of using acetate to deprotonate.
Yeah, if acetate is all you had, yeah, go ahead and use it for this. But if there's an amine present, that's a much better base.
But then shouldn't we have like excess amine present?
Well, it's catalytic acid, so there is extra amine present. It'd be a little, you rarely do a reaction with exactly one equivalent. You'd put extra amine in here, but I could put that down to help clarify it. So this is one answer. That the one I have on the key? Yeah, that's the one I put on the key. What answer did I not put on the key? Anybody think of it? Look at the product. There's an alternate way to draw that that's just as valid. It's actually a different compound.
You have the terminal alkene.
No, you're not going to shift the alkene, but you can have cis trans isomers because this is a free bond, a single bond that can rotate. You'd get a mixture of cis and trans, or E and Z in this case. Okay, that came up twice on the last exam. So just to make sure everybody's clear on this. Whoops, I don't want to do that. So at the top and the bottom are in essence the same reaction, but your starting material is in a different conformation and it gives the easy mixture of products.
So in general, if we're making a new alkene, should we always make or indicate both the E and Z products?
I would not always grade based on that. It depends on the nature of the problem. But in general, yeah. On the last exam, I said, show all products, right? And then you got to show it. Let's see. Yeah, this, don't worry about this specific reaction for the exam. This is kind of an extra challenge question just to see who could come up with this. I wouldn't grade anybody's homework down if you failed to find this, but we will see this on the next chapter. On the next chapter, no, on the last chapter. So this is looking ahead 2 chapters. It's called an enamine. Amine, like an all ether. Judy, you got another question?
Yeah, thanks so much. There was the one problem. I think it's labeled 15 in the answer key. We went over a bit the other day in class, and we figured out that the product actually was a little different than what was on the answer key. Yeah, I know it's there. It's that one there, 15, with the trimethyl orthoformate.
Yeah, I gotta sort out this answer key on here. There was some sort of a glitch here. I must have grabbed the wrong file. Yeah.
I'm feeling good with the mechanism now, but I was a little thrown off by like
yeah, I screwed up. My apologies.
No, it's okay. But the one equivalent of water is like the part of it specifically that I kind of wanted to address, because I was sort of hesitant to do too many moves involving water and hydronium because I felt limited by this notion of there being one equivalent of it. So I was trying to like kind of limit my mechanism to a certain number of steps. So, but the more I did it, the more I realized, you basically have to hydrolyze it to form.
There, I fixed it on the key. This, I got to remove the name now. This is one way I could have asked it, but that trimethyl orthoformate is not what that is. So when I change it, I'm probably going to change it to this because that would give this product.
Okay, yeah. But yeah, I was just wondering, like, how should we think about the limitations of one equivalent of water? Like, does that limit the number of steps that we can do with water, or?
Well, no, you can use water catalytically if you figure out a way, but this would protonate. It would lose methanol. The water would come in. You'd move the proton, and then methanol would come out again. So I have to change this to 2 methanols. Whoops, do that.
Yeah. Yeah, that's basically what I did.
Yeah, forgive me while I do the editing, because if I have a tendency to catch problems one year and say, oh, I'll correct it next semester, and then I forget.
So yeah, because I have, I guess, 2 steps where water either, well, there's one step where water attacks as a nucleophile. There's another step where water deprotonates.
Oh yeah, you can use the water as a proton transfer agent. Right?
Yeah. So really, we shouldn't think of
Yeah.
that.
When you see what I've written here, you should assume that one equivalent is reacting. But even if not, you're making methanol. Methanol is almost as good a base.
Mm-hmm.
And protonate methanol, same way you can protonate water.
Got it. Thank you.
Professor,
Yep.
I'm on question 8 now.
Oh, wow. Okay. So we should be done in time for me to have a good supper?
Yeah. So I had a similar mechanism to you, but instead of doing I attacked the carbonyl carbon with methanol instead of doing an intramolecular attack.
You can draw a nice, pretty mechanism that way that would be valid in terms of the way you did it, but entropy is going to win. The intramolecular will happen faster.
I see. So that's what I guess
Yeah, if this were a 10-point question on the exam, I'd be tempted to give you full credit, but I would take 1 point off.
Okay, so you would, because entropy favors the intramolecular reaction. So we would first protonate with a methanol that's protonated. We'd protonate the carbonyl carbon. Then we'd attack with the alcohol, and then
make the ring.
And that would make the ring, and then
sure
we would do a nucleophilic attack with a methanol group instead.
Yeah, first, you'd make the ring first and then bring the methanol in.
Right, so you'd make the ring and you would attack with methanol at the pi bond on the ring.
Mm-hmm.
Well, I mean, you showed us how to do it, but I just, okay. Thank you.
Yeah, I mean, several people did it backwards, which means you'd get most of the credit on an exam.
Okay, thank you.
On homework, I wouldn't take off for that as long as you wrote a note in your correction saying, oh, intermolecular wins.
Fair enough, thank you.
Which we are not doing for this homework, is that correct? We're not handing this one.
No, we're not handing this in, but I certainly hope you learn from your corrections anyway.
Oh, absolutely. I think this has actually helped me do it a lot more efficiently and like really identify where the problems are a lot faster.
Sure. I had a student once that came to me separately at the end of the year when the course was over, showed up at my office and said, you've helped me do better in all my classes because now I do all of my homework differently. Which is kind of my goal. Okay, we're going on 2 hours. I will go longer as long as there's meaningful questions. But there's a little doggy next to me wants her afternoon walk.
Professor, can we go over a question on recitation sheet 10?
Oh, sure. Recitation. So which one?
Oh, the last one. Is it because I remember you saying that you can't do sulfonation on an ortho position. If all the other positions, the para and the other ortho position is taken up, would it be
Yeah, I mean it has no choice. It has no choice. You just force it.
Then that's really all I needed.
Yeah, I mean, how easy would that reaction be to do? I think it would be a tough reaction, but it's about your only choice in making it here. So this is a problem I made up. I'm sure the first 3 steps are fine. That last step, it's a bit iffy, but it's all you have to try here.
Yeah, I was gonna put a like in parentheses forcing conditions.
Yep,
See if
that's
that would
great.
work.
I would love that little note. Yeah, and not being an expert in that specific area, again, I don't know how much you can force it. But methyl groups are tiny, right?
Professor,
Yeah.
I have a question about number 12 in homework ketone aldehyde.
Okay.
Yeah, in here we use dioxane, but I don't know what's the function of dioxane here.
It's a solvent.
Oh, solvent. Okay, okay, thank you.
Yeah, and that's what's missing from the key here. It goes from 11 to 14.
Yeah.
I lost those someplace. I'm going to have to redo that. I don't know where I lost those. Some glitch.
Thank you.
Yeah, dioxane was in the ether chapter. But it's just a solvent.
Okay, I need to check that again. Thank you.
Yeah. When solvents are particularly common, I like to throw them in now and then, just for awareness purposes.
Professor, for the recitation question that we just went over,
Yeah.
so in my answer, I did sulfonation before bromination because
Yeah, that would be acceptable too. I would switch those two without hesitating.
thanks. Okay.
Yeah, I admit right here in the answer key, this last step is the least certain. Yeah, good luck when you try it. It might take a special sulfonating reagent. So forcing conditions might mean a different reagent. I do have the capability of going into the database with this specific compound and seeing if anybody's made it before, but that ends up being a real time sink. Judah, you have a question?
Oh, sorry. I didn't realize my hand was still raised. But
yeah, well, I kind of ignored it for a while.
Sorry about that. I did have one quick question, also related to the previous recitation worksheet, which was EAS. It was EAS related.
Yeah, there were 2 on that, right? Because it's so much fun.
Yeah, and
there's a lot to put together in that chapter.
Yeah, and this definitely kind of helped clarify a lot of details. I was a little confused about the last problem, where we have no directing group really, and intuitively, part of me went right away to the product that you have there.
Okay.
But there are multiple ways, aren't there multiple ways of keeping 2 aromatic rings intact where there are 2 possibilities of
making... There are multiple ways of having a naphthalene, but not having 2 benzenes. There's a difference, remember.
Oh, please.
2 benzenes is 2 benzenes is better than a naphthalene.
Got it. Well, that clarifies it completely.
Yeah, just think of it as 2 more aromatic carbons.
Oh, right, because they're sharing otherwise.
We actually have seen this 3 times now, counting this. The very first time you guys saw this, oh, by the way, I do the starting material in the least forgiving form. Right? I'm not showing the double bond that is the one that needs to react, but I did show it in the product here. Okay, so when you draw the double bond in this position, it's a lot more obvious.
Sure.
So forget the sulfonic acid here at the end. That double bond reacts with bromine to give a dibromide. The only dibromide. What? An aromatic ring making a dibromide? Yeah, that carbon-carbon bond is less aromatic than all the others. So you can make a dibromide out of here. But then I mentioned that if you take the melting point of that dibromide, in the course of the melting point, it loses HBr. It goes aromatic again. So you can do electrophilic aromatic substitution on this. Isolate the dibromide intermediate, right? With no catalyst. So yeah, that bond is only nominally aromatic. You can hydrogenate this under normal conditions. That was on the last exam.
Right.
And you hydrogenate this double bond without using any type of special catalysts or anything. And this is the third case where phenanthrene just loves to react at these 2 carbons.
Got it. Thank you so much.
Okay. Yeah, the torture will continue until you guys get it. Anything else for today? If you guys continue studying and you end up with a question you're frustrated by, send me an email.
Do you have any more practice like problems or like worksheets or something?
I
Because it's nice to get
don't.
extra practice.
Um,
And your questions are pretty challenging, so it
but
really.
yeah, they are. They are. I push things a little bit. The worksheets I think are more forgiving. The recitations, but they still bring up the same types of issues, right? You have to decide which ring reacts first.
Oh, for that one, why doesn't nitrogen go on para?
Which compound? Which one?
Second question. Is
yeah, that would be an acceptable product.
Okay.
Yeah, I probably should show both. I think what I'm showing would be the major product in this case, though, because the aromatic ring on the left can help, but it has to be coplanar to help, and putting that nitro group will interfere. So, but if you put that, I wouldn't bat an eyelash. I'd say okay.
For one, my recitation teacher said a different answer.
What did he give you?
He gave me on the top, on the other ring, top left, top left, bottom
Well,
left.
the nitro ring is grossly deactivated. It's going to go on the bottom ring.
Yeah.
Left.
But he put the bromine on a different position. He put it on the.
He put it meta.
Yeah, he put.
Yeah, I won't argue with meta.
Wait, so it doesn't favor a specific position over the other?
It'd be a very good question here. You could argue either way. The argument. Let me put this in ChemDraw to be clear.
Because I drew the positive charges out, and you don't want the positive charge next to the nitrogen. You don't want the positive on the carbon next to the nitrogen.
So if you put it para, then the intermediate, where might I want to go? I don't use this as much. So then the positive charges on the sigma complex that I'm not showing are going to go, well, hold it. The nitro just got a positive charge in one of those resonance structures.
Yeah, so isn't this
So
unfavored?
is this aromatic ring truly activating or not? Okay, so if somebody wanted to argue with me and say the meta would be the major product, well, I wouldn't go into that argument. I'd say, okay, let's run the reaction, find out. So this is a tough one. So meta is entirely acceptable here in my mind. If we were going to do this one instead, then I'd say no, para. Okay, because now you're skipping the one the nitro group is on.
What about ortho?
Well, yeah, you get some ortho too.
Okay.
Okay, I thought I heard another voice interspersed there.
Oh, it was answered. I was gonna ask
Okay.
if the ortho product be.
Yeah, nope. Ortho, para, or mixtures, unless you know otherwise. Only 7 of you left.
Do you have any recommendations? I don't know why the hydrolysis mechanisms always get me. Like, I feel like once I've protonate, so I'm on number 9, right?
Which assignment?
Of 19.
I'm joking. How are you gonna find it here?
I know, I always know to protonate. I always know that the lone pairs next door will make a good, like the leaving group will go away on the positively charged oxygen. But then I don't know when water comes in again. Like I don't know.
Well, water is going to be your source of acid via the hydronium. It's going to be your base. And the oxygen will be the nucleophile whenever you make a carbon cation. So it serves 3 different roles here in reality.
And I think I just didn't.
Yeah, this is actually not very commonly used, but it is a protecting group. Which number is this? 9? Do I have it here? Yeah, I have it here. It's a workout, right? But it's a protecting group
For the carboxylic.
for carboxylic acid. This specific compound.
I see. Okay. So.
Yeah, and what we have not covered yet is the hydrolysis mechanism for esters. And I've included it here because if you just kind of get in the pattern, you're probably going to get it right. It's really not inherently different.
Okay.
So here's the ester, and by rights, maybe I should stop there. But hey, protonate and add water. The pattern continues.
Protonate, add water.
Protonate the carbonyl of the ester in the middle here. And now it's going to look a lot like what you've already done. Yeah, I'm not putting this on an exam. I don't want to grade this.
Okay.
But it's a great homework question for practice.
I think I'm better off doing the mechanisms for in terms of my use of my time for the next 2 days, maybe doing some simpler hydrolysis problems.
Sure. Just a simple acetal. You should be able to write that down. By just thinking clearly, it shouldn't be a struggle.
Right. Well, I'm good with that one spot.
But if you can do this one, you're good to go without help. Following it's one thing. If you can do this on your own, you got it. You know how to do all acid catalyzed mechanisms.
Thank you.
Maybe not all of them. I haven't even taught you guys about Ritter chemistry. You can protonate the nitrogen in a nitrile and get chemistry started, but we're not going to learn that. It again would be somewhat related mechanistically.
Professor, I have a last question before I go.
Sure.
For the test, you said there's 3 out of 5 questions on retrosynthesis that are challenging.
Yeah, there'll be 5 retrosynthesis, and I'm going to let you pick 3 of them. And I probably should do that more often Because if I just give you one and it's tricky at all, you might just get a mental block and now you're don't get much out of that question. So this one you can, kind of say, oh, I see that one. I see that one. Which one? Oh yeah, I see that one. And then you go with it.
So if I were to like answer all 5, but you would only grade the 3 that are the best grades, would you do that?
Okay, do it at your own risk.
So if I
If
do
you
all
make
5,
a
would you
mistake,
reduce
you make
points?
a mistake, I have to take off credit. You don't get extra credit. If you do it right, I'll give you a little extra credit.
Oh, really? Okay.
So how confident are you?
I don't know. We'll see.
I don't want to be grading extra ones for everyone in the hopes that somebody's going to get extra credit. So you got to make the bet that you can do it right.
So it's like a risk.
Yeah, hey, that's the way I'm making it, because I don't want everybody doing all 5 of them saying, I hope one of these is right, because I got to grade the things.
Yeah.
Fair enough?
All right. Yeah, that's my last question. Have a good day, Professor.
You too. Now we're down to 4 of you. And I can see all 4 names right now. My family should be home soon. I was alone with the dog last night. My wife and mother-in-law went to visit my daughter who missed family. So I don't think it's strictly within the Cornell COVID rules, but you discreetly pick them up, you go off campus. They've been mostly just hanging out together in the hotel. Okay, things are definitely going to slow down now. I'm going to turn off the recording.